Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 41. Determine the centroidal moment of inertia of the hollow circular section of a shaft of inner and outer radii of R sub I and R sub O respectively, with respect to the letter A x-axis and B y-axis. Also determine the polar moment of inertia. So for our solution, by the way, I'm going to derive the formula, although we already know that the moment of inertia of a full circle or circular area with respect to x, y, or any diameter is pi over 4 radius to the fourth. So therefore, for this hollow section, you'll have an idea that the moment of inertia is simply the moment of inertia, let us say with respect to the x-axis or y-axis of the big circle or outer circle minus the moment of inertia of the inner circle. That is pi over 4 RO to the fourth minus pi over 4 R sub I to the fourth. So that's the expected moment of inertia of this hollow circular section or this hollow shaft section, or the moment of inertia with respect to the x, y, or any diameter is pi over 4 quantity RO to the fourth minus RI to the fourth. Since by symmetry Ix is expected to be equal to Iy, then polar moment of inertia with respect to O, the center, is simply double the moment of inertia with respect to the x-axis or the y-axis. That is JO or IO or IZ with respect to the z-axis is equal to pi over 2 quantity RO to the fourth minus RI to the fourth. But we will begin with the derivation, assuming uh, you do not know the moment of inertia of a whole circle yet, but it is necessary that you should be able to remember the moment of inertia of a whole circle with respect to the diameter or x, y, or any diameter. It's the same. And the polar moment of inertia is simply the sum of the moment of inertia with respect to the x-axis and the y-axis. So this is our differential element. The distance from O to this element is r. That's the constant distance, small r. The thickness is dr. And by definition, differential Ix is equal to, or differential IO, that's derive the polar moment of inertia first, is equal to distance squared times differential area, where the differential area is the length of this strip. If you're going to cut it and flatten it out, it is equal to the circumference of this strip, that's the length, 2 pi r, and the thickness is dr, therefore the differential area is 2 pi r dr. So differential IO is equal to distance square, RO square, times differential area 2 pi r dr. Circumference, straight line, horizontal, let us say, circumference, then the thickness dr. So IO is 2 pi integral of r cubed dr from inner radius capital R sub I to outer radius capital R sub O. So the integral of r cubed dr is r to the fourth over 4. So IO is 2 pi quantity r to the fourth over 4 from r sub I to r sub O. So if we simplify this is simply pi over 2 quantity RO to the fourth minus RI to the fourth. So that's the polar moment of inertia, or JO. So therefore, I sub O is pi over 2 quantity R sub O to the fourth minus Ri to the fourth. And since this is equal to ix plus iy, and by symmetry, ix is equal to iy, or in fact, it is moment of inertia with respect to any diameter, then it is equated to 2 times ix or 2 times iy. Therefore, I sub x equals I sub y equals pi over 4 quantity r sub o to the fourth minus ri to the fourth. So that is I sub x. This is I sub y as expected. And I sub o is pi over 2 quantity ro to the fourth minus ri to the fourth. Now, in the mechanics of materials, most often the moment of inertia, especially the polar moment of inertia, is expressed in terms of the diameter. So if expressed in terms of the diameter, you just, if the outer diameter is capital D and the inner diameter is small d, you just replace r sub o by capital D over 2 and r sub I by small d over 2. And the result would be pi over 32 for IO or JO, pi over 32 quantity big diameter to the fourth minus small diameter to the fourth. So that's it. Level 42, this is in preparation to parallel axis theorems, which is very parallel axis theorem, which is very important in determining moment of inertia of composite areas or sections. And this area, which is rectangular, is very important, especially if we need to uh, consider composite areas where a rectangle is present, especially the moment of inertia of rectangle with respect to its centroid, parallel to the x-axis or the y-axis. So this is the rectangle. The dimension should be b by h. So we learned that with respect to the base, the moment of inertia is bh cubed over 3, or with respect to the upper base, it is still bh cubed over 3. While with respect to the edge, it is b cubed h over 3. On the right edge also bh cubed over 3. Now this time, we'll have to derive moment of inertia with respect to the centroidal x-axis, which is parallel to, of course, the base or the x-axis. And we use that result to write the moment of inertia with respect to the centroidal y-axis. So for the solution, uh, since we already know that the moment of inertia with respect to the base is bh cubed over 3, then with respect to this centroidal axis here, we just imagine or treat the upper rectangle and we consider this as its base. And since there are two identical rectangles, then we just multiply it by 2. While the height of the rectangle is, of course, half of h because this is the centroidal axis. So that's h over 2, h over 2. Therefore, IGX is 2 times I of rectangle with respect to the base, which is also the centroidal x-axis, which is denoted by G sub x. So it is 2 times the moment of inertia with respect to the gx axis of the upper rectangle. That's why we multiply it by 2, because the lower rectangle is identical to that of the upper rectangle. And we have here the common base. So formula is b height cube over 3, but the height that we're going to use here is half of h, because this is h over 2. So IGX is 2 times quantity b times h over 2 cube over 3. Since this is 8, 2 times 1 over 8 bh cube over 8 times 3, so 2 times bh cube over 24 is bh cube over 12. So from now on, remember that the moment of inertia of a rectangle, especially for beginners, is bh cubed over 12. You need to know this because we're going to apply this in parallel axis theorems in dealing with composite areas later on. Then likewise, IGY is b cubed h over 12. So IGY is 2 times IGX of the right rectangle, this rectangle here, where the base is b over 2 and the height is h this time. So it is b over 2 cubed times h over 3. So IGY is 2 times h or b over 2 quantity cube times h over 3. So simplifying, that is also b cubed h over 12. So take note that the moment of inertia with respect to the x-axis, this x-axis here for this rectangle is vh cubed over 3. Then with respect to the x prime axis, which is also the base, but the upper base is the same, bh cubed, ix prime is bh cubed over 3. I just discussed the other cases. So iy is b cubed h over 3, b cubed h over 3, then iy prime is the same. This is the axis, so it is also b cubed h over 3. So even if the orientation of the axis is different, the remember the corresponding formulas. So with respect to the base edge, it is uh, dimension cube the other dimension perpendicular to that axis divided by 3. But with respect to the centroid parallel to the base, it is bh cubed over 12 perpendicular to the base through the centroid b cubed h over 12. Level 43, let's also derive the moment of inertia of the triangular area with respect to its centroidal x-axis. Again, purpose is in preparation to parallel application of the parallel axis theorem, or when we deal with composite areas. So this is the triangle in general, and we have the base here. This is the centroidal axis parallel to the base. So remember that the centroid of that triangle is, if the height is h, is from the base, the location of the centroid is 1/3 of h. Then from the vertex, it is 2/3 of h as shown. So let's consider that strip. We will call the length of the strip as b1. The thickness is dy. And of course, the distance of the strip, horizontal strip from the base is y. So that the distance of the strip from the vertex is height minus y, or h minus y. Since we want to derive the moment of inertia with respect to this centroidal axis, we use distance squared times differential area, where the distance, this distance here, in general is equal to y minus h over 3. So even if the strip falls below, it is, the distance is uh, h over 3 minus y, or simply y minus h over h minus 3, although it's negative expected. But remember, it is to be squared, so it doesn't matter. So again, the distance is y minus h over 3, and the differential moment of inertia with respect to this axis here is distance squared times differential area, where the distance is y minus h over 3, then the differential area is b1 times dy. So for our solution, differential igx equals distance y minus h over 3 squared, differential area dA. Then we substitute dA, which is b1 dy. So differential igx equals quantity y minus h over 3 squared times b1 dy. We now express b1 in terms of y by these similar triangles. So from the figure, b1 as to h minus y equals b as to h. Therefore, b1 is equal to b over h, quantity h minus y. Substitute into this equation here, so differential igx equals quantity y minus h over 3 square times b over h minus y times differential of y. So simplifying, igx equals b over h integral of quantity y minus h over 3 square by expansion y square minus 2 thirds hy plus h square over 9 times h minus y dy. Then before integrating, we have to simplify this by expansion. Igx equals b over h integral 0 to h of quantity hy square, then minus 2 thirds h square y, then minus h square y over 9, sorry, plus h cube over 9 rather. We distribute this, h cube over 9, then y squared times negative y is negative y cube, negative 2 thirds hy times negative y is positive 2hy squared over 3, which is this. Then h squared over 9 times negative y is negative h squared y over 9, and dy. The variable of integration is y, therefore the limits would be from 0, from the base, y is 0, to the vertex, where y is h. So integrating, igx is b over h, quantity hy cube over 3. This is h square y square over 3, cancel 2. This is h cube over 9y minus y to the 4th over 4 plus 2 over 9 hy cube minus h square y square over 18 from 0 to h. So remember, these are like terms. Lower limits, don't mind, 0. So let's have the upper limits. Everything will be in terms of h to the 4th. So igx is b over h quantity h to the 4th over 3 minus h to the 4th over 3 plus h to the 4th over 9 minus h to the 4th over 4 plus 2h to the 4th over 9 minus h to the 4th over 18. Then lower limit 0. Minus everything would be 0. So this will be cancelled. So using the calculator, 1 over 9 minus h over minus 1/4 plus 2 over 9 minus 1 over 18. Then the result would be in terms of bh cube. So computing, igx is bh cube over 36. So remember that it is bh cube over 36. So if the triangle is oriented in this manner and we want to find the moment of inertia with respect to the sinusoidal y-axis, the moment of inertia would be b cube h over 36. So iy is b cube h over 12 with respect to the base, which coincides with the y-axis. With respect to the centroid, b cube h over 36. And I want you to remember that. Then for this orientation of the triangle, with respect to the x-axis, bh cube over 12. With respect to the centroidal x-axis, which is h over 3 here, bh cube over 36, igx. And with respect to the y-axis, b cube h over 12. With respect to the centroidal y-axis, b cube h over 36. So if the right triangle is oriented in the following manner, as shown, these formulas still apply. Take note, when the triangle is oriented in this manner, these are still the appropriate formulas. if oriented in that manner, these formulas are still the same, valid for that orientation of the triangle. And if that right triangle is oriented this manner, these formulas are still applicable or applicable to this triangle, orientation of this triangle. So that's it, and I hope that uh, you can recall moment of inertia with respect to the centroidal axis of our rectangle is b parallel to the base of bh cubed over 12, then perpendicular to the base b cubed h over 12 for rectangle with respect to the centroid. Then for triangle, with respect to the centroidal axis parallel to the base bh cubed over 36, with respect to the centroid perpendicular to the x-axis, which is the y-axis, b cube h over 36. But with respect to the base, bh cube over 12 or b cube h over 12 for base that is coincident with the y-axis. So that's it, and I hope you can remember that, as well as for circles and quarter circles, uh, which will be derived in the next part.